Yeah, today we're going to talk about Golgi, the performance-aware, resource-efficient function scheduling for serverless computing. And I guess I'll spend the first few minutes just talking about the like a general, like abstract, high-level overview of the serverless computing. Right? Because like yeah, that will make it easier to understand like what exactly this paper is proposing. Right? So in a serverless computing framework, you essentially have functions that run somewhere in the cloud, right? So you compose your applications from many kind of standalone functions, right? So some pieces of code that will do some computation, potentially on some data that you store somewhere else in the cloud, right? So a typical workflow of a single function invocation is going to look like this, right? So you'll have a client, right? And this client will send a request, let's say maybe to run a function X, right? And this request will go to the serverless platform. I will put a box here. And this serverless platform will decide, essentially, will figure out where to run that X, right? So this platform, you can think of it as having like a scheduler inside that is aware of like what machines it has and what machines are capable of running particular function X, right? So somewhere in this platform, there is going to be a scheduler component, right? We can also think of it as load balancer as well. And scheduler is going to say, okay, I got the function X. I know that there is a server. Let's say this is a server I put in red. And this server has a container for function X, right? Maybe it has another container for function X, but this one is running, right? So this container is busy, but this one, the top one, is empty, right? So the scheduler will say, hey, sure, go and run X here in this lovely empty container, right? So from the resource usage standpoint, right? So this red server obviously has some finite capacity, right? It has finite CPU, RAM, and other resources, right? And the functions, when I call function X, that function is registered somewhere in that serverless component. And when users register this function, they say, sure, I want this function X to be run when users invoke it. And when you run this function X, it needs to have some resources available to it, right? So usually that would be something like specifying amount of RAM, for example, right? So you may say that X needs 4 GB of RAM, and then the serverless platform will create those containers, right, with specific size, right? So maybe 4 GB and then, I don't know, 1 vCPU, right? So typically, you specify one resource, let's say memory, and the other resource, like the CPU, will scale proportionally with memory, right? So what happens, however, is we don't only have function X, right? There is also functions Y, Z, A, B, and whatnot, right? So this platform will have on the same box, it may have other other containers for other functions, right? And they may be different sizes as well, right? And a lot of this, again, you want these containers to be used, right? So you don't want to have like empty containers waiting for function invocation. So you tend to have like as little unused containers as possible, right? Because you want the function to arrive to empty one and then be busy, right? So you want to have just enough empty slots to run each function as there is workload, right? Obviously, if the workload changes, the scheduler and the load balancer in the serverless function will, maybe add more access, right? Maybe on some other machine, as it needs to, right? But like again, the idea is to have like just enough spaces to accommodate the workload as it happens. So, yeah, that's kind of the general overview, right? Of like super high level view of how cloud computing platforms may work. What this paper is saying is that obviously this resource provisioning is it's very static. So when the engineer said that the function X needs to use some particular amount of resources, let's say 4 GBs of memory, that's kind of it, right? And if we provision 4 GB, then there is a chance that we will actually like not use that 4 GB, right? Because engineers, they tend to be greedy, right? So they tend to ask for more than they actually need, right? So the reality is, like if we follow those specifications that engineers provide for resource consumption of their functions, our servers, they may be, they may be, they may become under provisioned, right? So that's not good for, from like resource utilization standpoint, right? So that wastes the resources of the cloud provider, that wastes the, electricity and like, whatever else, the data centers need, right? So you want to pack those functions into those servers as tightly as possible, right? But following those prescription like usage, like resource usage from the engineers doesn't allow for that tight packing, right? Because again, like my engineer may say that function X needs 4 GB, but if you look at how much memory function X actually uses, maybe it's 2 GB on average, right? So, you are on average throwing away some resources out just because the engineer said so. So what happens is that cloud providers, serverless function providers, they tend to over-provision, right? And the typical strategy for over-provisioning is to just look, the historical data, like how much resources each function used, and scale your containers down to that amount, right? And if at some point the function needs more, then you may need to like adjust, right? You may need to restart it in a bigger container if you, for example, run out of memory and got an error, right? So, but by kind of scaling the container, so the VMs that run those functions down to an actual observed resource usage as opposed to prescribed, the function registration is like one way to pack those tighter. The problem is, of course, that may impact the performance, especially the tail latency, right? So one thing is, when we look at that, like scaling the VMs or containers down, we tend to still like a little bit more resources than that average observed resource usage, right? So that there is like at least a little bit of headroom on average. But there is like another problem that the authors of this paper talk about, and like the performance of those functions and like their tail latency is being impacted not only because you start to over provision your resources, right? So for you start putting those functions into smaller containers than what they supposed to run on, but you also have like a mix of workloads, right? And you specify those container sizes only in terms of, let's say, memory and CPU. But there are other resources that um, um, uh, yeah, there are other resources that we need to consider, right? And that's what like this paper argues. So one of these resources that they want to consider is shared network, right? So when you say the function uses 4 gigabytes of memory and 1 CPU by the ratio between the memory and CPU. What about the network? How much network does this function use? How much data does it needs to like a request from some storage or from the users? How much data does it produce and so on, right? Because if you have the X function here that uses a lot of network and the Y that uses a lot of network and Z that uses a lot of network, right? You may create the interference even if on paper they all have good like amount of RAM and CPU available, right? Because there is like this other resource that is not accounted for, like the shared network, network interface, network card. Another one that is like very interesting that they look at is CPU cache, right? Especially like a L3 cache, right? The one that can be that's shared between the cores, right? So if a particular function is like needs a lot of like memory bandwidth, right? It will use more cache. You want to call function X, Y if they both like memory intensive functions that heavily rely on cache, right? Because now running them will interfere. Like running them at the same time on the same machine, will create like performance problems, even if we don't account for any other resources. So Golgi accounts that. They try to account for this, right? So they say we are going to over provision the servers, right? Meaning that we're going to have the containers that are smaller based on the observed usage. Now, we're also going to have containers that are the right size just in case, right? But then we also control how we place those containers to avoid some of those destructive things like having too many functions that use network at the same time and content on this other resource that we don't control by default. And what they do in this scheduler component, right? They put a little ML model, a binary classifier that pretty much says that pretty much checks if the function X, like as you're trying to schedule the function X, um, um, can it be scheduled in like any of the existing spots, let's say over provision spots, right? Based on the degree of over provisioning, right? So how much did we shrink those containers and the other things going on, right? So this ML model, this classifier essentially gives you a yes or no answer, right? So, and it's trained online, right? So as you, let's say, start to put, as your workloads change and you put like more functions that, for example, use a lot of network and X is using a lot of network, right? Then, the same container that you use that used to work fine, right? Even though it's like over provisioned, it's a smaller size than you prescribed, but it used to work fine. But now because the workload in the cluster itself changed, now there are more other functions that can depend on those other resources. You may not be able to use that same container and still satisfy your like latency guarantees and get a good tail latency, right? So they have this like binary classifier in their scheduler that will just tell you, hey, am I good to go in this particular situation, given the other things going on in like on that machine, right? So that's kind of a super high level overview of what's going on. I think I want to maybe switch to the paper now, so I'm gonna stop sharing the whiteboard and share the actual paper. So they have this thing, so they characterize those things that can interfere, right? So as I mentioned, they consider the network, right? The network, the CPU cache, and then they also obviously consider, the traditional things like the CPU usage, in addition to those collocation interference, the CPU and the cache. Right. So, yeah, the way their protocol scheduler works is it has that model, right? That machine learning model, and that model is trained online as the workload changes. So they use a forest of trees, right? So a type of a forest model, which is supposed to be like very lightweight for like near online training, right? So as new workloads come in and as those servers like the workloads on the servers and the machines change, that model gets updated, right? And that model is trained in a sense to figure out like at what level of all these resource usages, like how much can you over provision the CPU and memory, and how much can you like how much of the cache and network sharing can you do, right? So it takes this like the vector of all the resources and just tells you, okay, for particular server for this workload, yes or no, can I put this function in that server, right? And if the answer is no, if you cannot put it there, then you just pick another machine that you can, and you can also pick a machine that's not over provisioned entirely. They also talk about the scalability aspect. So there is a vertical scaling, right? So they say that because of that ML nature, right, they can misclassify something. So they may say that something is good to go on the machine, but in fact it will not. So they also want to like scale vertically very aggressively in terms of like the containers. I wouldn't call that their scaling is like very vertical. What they do is they provision a container or VM that can run multiple function invocations concurrently. And when they need a vertical scaling, then they just reduce the concurrency limit. So the same machine, the same container now just serves fewer functions at the same time, so that each concurrent, function run has more of that container's resources shared. Yeah, I think I'll stop at this point. We can talk about this.